A product risk matrix helps compare susceptibility across oils, balms, creams, lotions, shampoos, cleansers, eye area products, and botanical formulations. The main control focus changes with water phase, repeated use, packaging, raw material variability, and consumer exposure. Microbial survival depends on water availability, pH, preservatives, surfactants, oils, alcohols, chelators, nutrients, and product structure. Analysts should ask whether the product supports growth, survival, or only transient contamination, and whether the matrix interferes with recovery. Water activity is a major reason why some products are more susceptible to microbial growth than others. Low water availability can reduce growth, but it is not automatic safety because molds, yeasts, surface contamination, packaging, and consumer water exposure may still matter. Preservation is a complete product control strategy rather than a single chemical in the formula. It depends on formulation design, preservative selection, compatibility, challenge testing, manufacturing hygiene, packaging support, and stability through shelf life. Preservatives may fail because of high initial bioburden, pH drift, ingredient interactions, poor mixing, consumer use, or loss of activity during storage. These failures usually reflect a system weakness, so investigations must review the whole control design rather than only one ingredient. Challenge testing evaluates whether a product can reduce or control defined microorganisms under method conditions. Neutralization and recovery are critical because the method must recover organisms when present, and results must be interpreted with the product, packaging, and intended use in mind. Microbial limits testing estimates viable contamination in products or materials under defined method conditions. Representative sampling, appropriate homogenization, neutralization, suitable media, incubation, and accurate reading of plates are all essential control points. Neutralization prevents preservatives and antimicrobial ingredients from continuing to suppress microorganisms during the laboratory test. A suitable method must recover organisms in the product matrix, use appropriate diluents and controls, and document recovery performance clearly. Sample preparation depends on the product matrix, including liquids, creams, shampoos, powders, wipes, oils, and balms. The analyst must choose a method that disperses the sample, controls foaming or phase separation, neutralizes interference, and produces a representative test portion. Enumeration is both a colony counting task and a documentation task. Select countable plates, calculate results accurately, confirm controls, review trends, and report the result in relation to the sample type and specification. Target and objectionable organism screening focuses attention on organisms that matter because of product use site, consumer population, or recognized risk. A low total count does not remove concern when a specific organism is detected, especially if isolates repeat or match a known contamination route. Cosmetic microbial spoilage can present as gas, package swelling, off-odor, color change, visible mold, texture shift, or cloudiness. These signals should trigger targeted testing and investigation rather than being treated as cosmetic defects only. Raw materials are an early opportunity to build microbial quality into the product. Botanicals, clays, proteins, gums, sugars, natural powders, water-based premixes, and exposed packaging components often require stronger supplier control and risk-based incoming strategies. Water is often the most important microbiological utility in cosmetic manufacturing because it enters formulations and supports cleaning and transfer operations. Routine sampling, trend review, sanitization, hygienic design, and control of hoses and outlets help prevent repeated process seeding. Environmental monitoring in cosmetic facilities should be risk-based and designed to reveal hygiene status and contamination routes. Sampling may include product contact surfaces, filling zones, water points, drains, hoses, tools, gloves, garments, and air where open exposure is relevant. People can introduce contamination through gloves, clothing, movement, direct handling, and unplanned interventions. Good hygiene requires controlled gowning, hand hygiene, glove changes, careful movement, and immediate reporting of deviations around exposed product. Cleaning removes residues, while sanitization reduces microbial contamination, and both must be suitable for the process and product. Residues from oils, waxes, polymers, surfactants, and powders can protect microorganisms when cleaning is incomplete. Packaging can reduce risk through pumps, tubes, single-dose packs, airless systems, tight closures, and protected components. Open-mouth jars, finger contact, bathroom storage, damaged closures, contaminated applicators, and consumer dilution create repeated opportunities for recontamination. Welcome to Module 12, Cosmetic Microbiology Fundamentals. This module connects product design, preservation, manufacturing hygiene, testing, and consumer use to practical microbiological control. Cosmetic products are microbiological systems because formulation, packaging, user behavior, and the environment all influence contamination risk. Effective control protects consumer safety, product stability, shelf life, and brand trust. Cosmetic microbiology covers microbial limits testing, preservative efficacy, water and environmental monitoring, and complaint investigation. It links laboratory evidence with formulation, manufacturing, packaging, hygiene, and risk-based quality decisions. This module follows a practical journey from product risk and microbial threats to preservation, testing, control strategy, and investigation. Start by understanding why products can support survival, then connect the science to data interpretation and practical decisions. Microbiological contamination can affect safety, odor, color, texture, stability, and customer confidence. It can also trigger product rejection, batch investigations, consumer complaints, or recall risk when vulnerable users or objectionable organisms are involved. Cosmetic risk is product-specific, so a dry powder, a water-rich lotion, and an eye area product do not have the same microbiological profile. Water-containing and repeatedly used products often require stronger attention to preservation, packaging, and hygiene. Cosmetic laboratories consider bacteria, yeasts, molds, spore formers, and objectionable organisms in the context of product use. Correct classification helps select suitable media, incubation conditions, interpretation logic, and likely source investigations. Microbial risk in manufacturing can come from water systems, hoses, tanks, filling lines, equipment, personnel, dust, and packaging components. Clean process flow and protection of product contact points are essential to prevent contamination before filling. The Cosmetic Microbiology Laboratory manages sample receipt, preparation, dilution, neutralization, plating, incubation, counting, and reporting. Its data support release decisions, investigations, product development, and ongoing quality monitoring. Microbiology is connected to the consumer experience because contamination can affect odor, texture, color, and stability. Laboratory data should therefore inform formulation, production, packaging, QA decisions, and complaint investigations. A cosmetic microbiology analyst combines aseptic technique, method discipline, careful observation, and product risk thinking. The analyst must recognize interference from the product matrix, document abnormal growth, and escalate unusual findings with clear facts. A plate count is useful only when it is linked to sample identity, preparation, method suitability, and product risk. Meaningful interpretation considers product characteristics, dilution and neutralization details, countability, specifications, and historical trends. Microbial quality must remain acceptable through manufacturing, storage, distribution, and realistic consumer use conditions. Stability programs should connect counts, target organism status, preservative performance, physical changes, and complaint trends across the shelf life. A strong contamination investigation confirms the result, protects the batch, identifies the organism, reviews history, traces the source, and defines preventive action. Evidence should include product and batch history, water, environmental, personnel, cleaning, packaging, filling, and maintenance data. Root cause categories include raw materials, water, equipment, personnel, environment, and packaging. Organizing evidence by category prevents premature conclusions and helps the team compare organism identity with supplier trends, water data, swabs, records, and process events. Cosmetic microbiology data must be traceable, accurate, complete, and reviewable. Record sample identity, method, media, incubation, calculations, observations, controls, deviations, retests, investigation links, and clear final review status. Trending transforms individual results into practical knowledge about process health and future risk. Useful views compare counts and organism groups by product, line, room, equipment, raw material, supplier, season, campaign, water signals, environmental data, complaints, and stability. Rapid and alternative microbiological methods can provide faster screening, earlier signals, and useful investigation support. They still require scientific justification, method suitability, validation, defined interpretation, and careful attention to product matrix interference. Cosmetic microbiology decisions are guided by product risk, internal procedures, and applicable regional or international requirements. Professionals should never quote a limit without product context, ignore an objectionable organism because the count is low, or use an unsuitable recovery method. In the contaminated lotion case, first hold the batch, verify controls and sample preparation, and identify the isolates. Then compare the organism pattern with water, equipment, environmental, raw material, and bulk hold data before defining the impact and corrective action. In the jar cream mold case, determine whether contamination was present before release or introduced during consumer use. Review packaging design, retain samples, preservative performance, comparable storage, and whether the complaint is isolated or part of a wider market trend. In the preservative challenge failure case, review formulation, pH, preservative availability, ingredient interactions, water activity, and phase distribution before retesting. Improve raw material quality, manufacturing hygiene, or packaging design through a scientifically justified change rather than relying only on a higher preservative level. This activity asks learners to build a risk profile for a cosmetic product and connect design choices with microbiological control. Consider formulation factors, contamination sources before and after opening, main test types, controls, packaging improvements, and process control changes. Cosmetic microbiology connects product design, testing, preservation, manufacturing hygiene, packaging, and consumer behavior. A skilled microbiologist interprets data scientifically and practically, uses trends and process history to trace likely sources and support safe, stable products throughout their life cycle.